All right, so we're going to start off with finishing the notes from section B. Kind of cheated, left one out, didn't tell you what the other period was. So the other equation you need is period equals 2 pi square root of the mass divided by the spring constant. I left that out. It's okay. I think you picked it up in class. So that being said, let's move on to the section 3. Wave. Wave has to have some median to or disturbance of energy. It can be a discussion, whether it's water, wind, it's all waves. Even light can be described as a wave or a particle. So there has to be some medium. In other words, like when you look at sci-fi movies and there's always a great explosion in space, it's like, oh, cool. And you hear this giant rumble, and it's going to happen. There's nothing out there. So you cannot transfer the sound energy in a wave, sound wave, to you. It looks like a pretty cool flash of light, and that's about it. So, sorry, sci-fi movies lie. So, mechanical waves need a medium. Electromagnetic waves, light, do not. So that's your one thing. And just as I said, light can be traveled through space. Mechanical waves cannot. All right, pulse wave, periodic wave. Pulse wave is one single, if you would, thud, if you could, and then a periodic wave is a simple harmonic motion. Dun, 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 dun. Waves on an ocean are your periodic. A pulse wave is one explosion one time. So, simple harmonic is called a sine wave. They actually have sine wave generators. So that's where we'll spend a lot of our time with periodic waves and simple harmonic motion. So, simple harmonic motion, wave motion, sine. So it's basically flipping this little rope up and down. If you notice, at a certain point in time, A goes from the center, then it goes up, then it goes back to the center, and then it goes down. Up and down, side to side, whatever it is. It's simple harmonic motion. So, some simple definitions that you should have remembered from physical science. Again, I know you probably didn't. I got it. Transverse wave, that's what typically everybody sees. This is a transverse wave. So, from top to top or crest to crest is basically a wavelength. Also, it could be from trough to trough, the bottom to the bottom. The amplitude is the measure of x all the way out to the edge. Can be from low or high, to the crest, to the equal, or from the equilibrium line down to the trough. Either way, still wavelength. So, longitudinal waves. This is where you like pushing a slinky. To be fair, that's the only explanation I've got of it. It is actually one of the ways that ground moves in an earthquake, but other than that, very few times I've actually seen this. So, and you can see the picture. This one's all scrunched up. This is stretched out. This is normal. This is scrunched up, normal, stretched out. So if you look at the density diagram, you can see the difference. High density are crests, low density are troughs. So longitudinal waves, think of a slinky. Frequency, period of wave, simple definition. They are inversely related, which will come in handy because, well, frankly, wave speed, we've done this before. Speed of light equals frequency times wavelength. The wave speed we've used in the past is the speed of light, 3.00 times 10 to the 8th meters per second. We will use different speeds of light, or different speeds. Not so much different for speed of light. But. Transfer of energy, basically you're transferring vibrations, which is an energy. The waves. Superposition, basically when you have two waves coming in the same space in the same time, can either be destructive or constructive. Example, A comes here, big wave going that way, little wave going this way, comes together. You can see there's the little one, there's the little one, but when they get together, they actually construct to form a higher level, and then they split, carrying their initial energy with them again. So there's constructive interference. Likewise, destructive interference, going that way, you can actually see the actual impact. One used to be here, one used to be here. And then again, they keep going with their same energy. Now, this is where it becomes interesting. I've never seen this situation on the left other than when something's roped off to something. I've seen it using it on the farm. for a horse and to pull some rope, but that's about it. I know oil rigs use it to actually move rope and chain, but other than that, I have no idea when it would be used. So if you have an idea, let me know. Second hour, the fixed boundary. Fixed boundary is actually what happens a lot. People do this with garden hoses, trying to get it to move around something. You put a pulse one direction, and then it hits the fixed boundary, and it comes back. Garden hose is the easiest example of this. So, standing waves. A node is basically where it is zero displacement, and you'll see that here in a second in the picture. Antinode is basically where it's the largest. Kind of interesting. We'll play with these a little bit. So, example, node, node, antinode. Here, a node, a node, a node, antinode, antinode. That being said, the distance, number of waves are included in 2L. So this gives you where the diagrams are. So like this one, for D, has 1, 2, 3. So, all right, last picture. Actually a string generator, a wave generator on a string with a black light. It's kind of one of those things you can do. Don't pay attention to those numbers, we'll get back to those. But that being said, that's actually what the string's vibration look like when you have it. The blue line is not the important, it's the orange. It's pretty cool. So that wraps up notes for chapter 11. We're going to do a little bit more practice in. Don't forget to do the check on learning.